In this video we begin our exploration of vibrational spectroscopy. This first slide shows the electromagnetic spectrum with corresponding wavelengths and photon energies. We know from our discussion of the quantum mechanics of vibrational motion that energy level spacing corresponds to the infrared region of the electromagnetic spectrum. When light interacts with molecules, the dominant form of that interaction is the oscillating electric field oscillating or interacting with the charge density of the molecules themselves. This slide shows the different types of interactions or transitions that can occur when a photon interacts with the energy levels of a molecule. The first one here is absorption. In absorption, we have a molecule starting out in the lower energy state and moving to the higher energy state after it absorbs a photon of light. Spontaneous emission occurs when it starts out in the higher energy state and ends up in the lower energy state. The molecule loses energy and emits a photon in that particular circumstance. Finally, in stimulated emission, we have a circumstance where a photon comes in with an energy equal to the spacing between the energy levels. The particle, being in the higher energy state, is then stimulated to emit a photon as it comes down to the final state. The key here is that we have one photon coming in and two photons coming out, so that we've actually created an additional photon. This is the principle behind laser radiation, and we'll talk a little bit about this later in the semester. To understand the intensity of the interactions between these light and the energy states of the molecule, we need to look at the population distribution of molecules amongst the various energy levels. The Boltzmann distribution is used to calculate relative populations between molecules in different energy levels at a given temperature. That is given by this equation here. All right. The various terms in this equation, P represents the population of a particular energy level. The G's in this equation represent the degeneracy of levels, and we'll be talking about that later on. E represents the energy of the given different terms. K is the Boltzmann constant, and T is the corresponding temperature. Let's look at a specific example. Suppose we consider carbon monoxide. The wave number corresponding to the vibration in carbon monoxide is given here as 2170 wave numbers. What we're going to do is we're going to compute the population ratio between carbon monoxide molecules in the n equals 0 and n equal 1 states. So we'll use the Boltzmann distribution to do this computation. Here are the equations for the energies of the various n levels for the vibrational motion. The equation here on the left is in terms of the frequency of the vibration, nu. The equation here on the right is modified so that we can use wave numbers instead of frequency. In this case, when we do the calculation, we find that the energy corresponding to the 0 level is given here. The energy corresponding to level 1 is given here. What about the degeneracies? Well, for diatomic molecules, the vibrational energy levels are non-degenerate, so the degeneracy factors for both levels correspond to 1. Plugging these numbers into the Boltzmann equation gives us this expression here, and when we substitute degeneracies, of course, this ratio here is going to be equal to 1. The only thing we need to know is the temperature. So we're going to compute the temperature at a particular value. Let's start at 298. We find that the ratio of these levels at 298 kelvins, close to room temperature, is on the order of 2.8 times 10 to the minus 5. Meaning there are far more molecules in the n equals 0 state than in the n equal 1 state at room temperature. If we move on to 1,000 degrees, we find that that ratio has increased, that now the ratio is 0.04 so that there are far more molecules in the n equal 1 state than was the case at 298 Kelvin, but still there are many more molecules in n equals 0 than n equal 1. One thing that's important to note is if the degeneracies are equal to 1, that is, if the molecules are non-degenerate in all the levels, there will always be more molecules or a higher population in the lower energy state than the higher energy states. This table shows population ratios for various molecules. If we look at room temperature right around 300 Kelvin, we'll note that by far there are more molecules in the n equals 0 state, as mentioned above, than the n equal 1 state. If we take a look at the bottom one with bromine, which has a 323 wave number spacing, which is much smaller than the others, we still see that the ratio is 0.2. There are far more molecules in n equal 1, but it's still less molecules in n equal 1 than n equal 0. And again, that's due to the degeneracy issue. Meaning that, of course, that all of these levels are non-degenerate. If we do a simple comparison here, we'll certainly note that as we go down this particular table, that the wave numbers are decreasing, and that means that the spacing between the energy levels is decreasing, and as the spacing decreases, the relative population that we see over here increases in that order. And of course, if we compare to the 1000 Kelvin values, we'll note that the proportion of molecules in n equals 0 and n equal 1 relative to n equals 0 does increase as we go to the higher temperature. And that should make sense. As we heat things up, there are going to be more molecules in the higher energy states. This ends our discussion of vibrational spectroscopy and the Boltzmann distribution. Our next video will detail the quantum mechanics of the vibrational spectroscopy in the harmonic and anharmonic oscillators.